So here we go, guys, 15E.2. We're continuing with kinematics, and this is a good example of how far the kinematics will go when we get to stage 2 level. We're just going to get straight into the question, and then we can address some of the content above about speed and so forth. So what we remember is we have S of t, and this is a displacement function. It tells you the position of some object or particle with regards to time. So we have a particle moving along the x-axis, and its position is given by this function. T to the 3, take 9t squared plus 15t. Okay, part A. Draw sign diagrams of the particle's acceleration and velocity functions. So we know velocity, the velocity function is the derivative of the displacement function. So if this is the displacement function, we're just going to differentiate it. That's going to be 3t squared, take 18t plus 15. Okay, now we want to draw a sign diagram of the velocity function. So I'll go through this one manually again, but then we'll look at how we can use the technology to support us. So first we need to find the roots, right? We would find when it equals 0. And if I'm looking along here, I can see 3 is common to all of those. So first thing I'll do is factorize 3. And then we've got this quadratic that we're looking to factorize, right? Two numbers that multiply together to give us positive 5. When we add them together, we get minus 6. That's going to be t take 1 and t take 5. Okay, minus 5 plus minus 1 is minus 6. Apply the null factor law, we'll get t is 1 or t is 5. So they're the values that make the velocity function equal to 0. So if we're drawing a sign diagram in kinematics, remember, we only consider positive values of time. So that line there, here, this means time is 0. And we have a root at time is 1 and a root at time is 5. And then we're going, when is it above, when is it below? Well, it's the equation of a quadratic. It has a positive a value, which means it's going to open upwards. It's got a happy face. So it goes from above to below to above again. Okay, let's demonstrate this on the calculator. Remember, if you have a function, t to the 3, I'll use x, sorry, x to the 3, take 9x squared plus 15x. Okay, I'm going to call it f of x. Remember, you can use your calculator to graph f dash of x. Okay, you can use your calculator to graph the derivative. And if we look at the graph of the derivative, we can see it has a root at 1 and a root at 5, and it goes from above to below to above. So we can get all of that straight off our calculator. That's absolutely fine. Here's the technique that we learned last semester to establish that. Okay, so that's the first part. We've done the velocity sign diagram. Next we need to do the acceleration. And acceleration is the rate of change of velocity. So all we need to do to get the acceleration is differentiate the velocity function. So when we're differentiating, here we've just got different arrangements of it, right? I'm not going to differentiate this one because it's in brackets, so I'd have to expand it out. Here we've got it fully expanded, everything's expressed to the power n. So this is the function we're going to differentiate. So 3t squared would become 3 times 2t. 18t becomes 18, and the 15 disappears, right? So this is 6t, take 18. That's the acceleration function. Now for us to draw the sign diagram of the acceleration function, we need to know what's the root. When does it equal 0? So we'll have 6t is 18, and we'll have t is 3. Divide both sides by 6. All right. So the root on the acceleration sign diagram is 3. So I'm going to draw that one here. We only consider positive values of time, so we don't need to sketch it for anything less than 0. And we need to demonstrate if it's going, where it's positive, where it's negative, right? So I'm looking at this and I go, this is the equation of a line. It has positive slope, which means it's going upwards, which means it comes from below to above. Okay? Similarly, we can see that on our calculator or on Desmos if I sketch the second derivative. Just by putting another dash in, f dash dash, that means we're differentiating it twice, d squared y on dx squared. Here it is here, or I can graph the function like this, 6x take 18, it's the same function. Okay, so you can use your calculator to support you to generate those sign diagrams. So that's part A, that's complete. Any questions? Part B, find the particle's position and time when it changes direction. So a particle changes direction when its velocity sign diagram changes sign. If you look at this, this is the velocity sign diagram, right? Now, when we have positive velocity, that means we're moving to the right, we're moving in the positive direction. When we have negative velocity, we're moving to the left. We have negative direction, right? So if we have positive velocity, and then we get to t is 1, and then we have negative velocity, it's changed direction. Changes direction when time is 1. And then you can see we've got negative velocity, and then we have positive velocity. Well, it's changed direction again at time is 5. So to answer part B, it wants the position and time when it changes direction. So for part B, changes direction at t is 1 and t is 5. How could we determine its position when it changes direction? Well, this is the displacement function that tells you its position for any value of time. So we want to know what's the displacement when time is 1. We're going to find s of 1. We put the number 1 into the displacement function. We put the number 5 into the displacement function. Now, you don't need to write all this out, especially when you've got 5 in there, or sometimes you've got fractions as well. It can take a long time. So I'm going to write it out, but I'm just going to get the answer. The fastest way to get the answer is straight off your graph. If you remember, we've got the original function here, and I want to know what's the displacement when time is 1. So I'm doing a y calc. When the x value is 1, I've got the displacement is corresponding y value, 7. So I've got s of 1 is 7. And you can see that's true. 1 take away 9, okay, that's going to be minus 8, plus 15, you get positive 7. Okay, it confirms it. Similarly, when we put 5 in, okay, I want to do a y calc when the x value is 5. Down here, we've got minus 25. Okay, so the particle changes direction when time is 1. Its position is 7 meters. Is our unit meters? Meters, 7 meters to the right of the point of origin. And when time is 5, it's 25 meters left of the point of origin. All right, we'll sketch that up on a motion diagram in a moment. Okay, so that's part B complete. Part C, find the particle's position and time when it changes direction. Sorry, we did that. Part C. When is the particle's, part 1, speed increasing? Okay, speed, we're looking at the second dot point for important points. Speed is the magnitude of velocity, and so that just means you don't consider direction, you just consider how large it's getting. So if B of t and A of t have the same sign on their sign diagram, then speed is increasing. So let's have a look. This is why we draw both sign diagrams. Okay, here's the V of t sign diagram, here's the A of t sign diagram, and we're saying for what intervals are they both negative or both positive? So if you look, between time is 0 and time is 1, okay, they're opposite. All right, this one's positive, this one's negative. But between time is 1 and time is 3, they are both negative, right? They're both negative over that point, so that means the speed is increasing over that point. Speed is increasing when they both have the same sign. So the first point is between 1 and 3. All right, between 1 and 3, I'll draw some vertical lines downwards. But you can see between here and here, this one's negative and this one's negative as well. All right, so the speed is increasing. The magnitude of velocity is increasing. Okay, and then the second point, all right, they're both positive after time is 5, right? They're both positive after time is 5. So speed is increasing between this interval and over this interval. All right, because they're both positive for values of t larger than 5. Now you notice this interval notation, right? When we first learned it in semester 1, we would have like 3 steps in order to generate a statement like that. So if that's a skill you need to revise, please let me know. But right now we're just sort of jumping straight to the conclusion, right? So just assuming that we remember how to do that. Let's move on to part 2. When is the velocity increasing? Velocity is increasing when acceleration is positive. All right, so velocity is increasing when the acceleration is positive. This is the acceleration. Acceleration is positive for time values larger than 3. Okay, so we have speed is increasing when they have the same sign. Velocity is increasing only when acceleration is positive. All right, part D. Find S of 6 and draw the motion diagram over the first 6 seconds. Hence, find the total distance travelled by the object in the first 6 seconds. So I'll keep moving down, I think, or maybe I'll might clear this part off. All right, so I'll leave that part up there, plus 15t. All right, so for a motion diagram, we're going to need the point where it starts. When time is 0, what's its position? So if I put the number 0 into this equation, the position is 0. We've already got S of 1. We saw that that was 7. We've got S of 5. We saw that that was minus 25. And we've got S of 6. That's what we're asked to find in this part. So I'll find S of 6 quickly, and then I'll talk about why we've chosen those points. So on the same function, when the time value is 6, the displacement is minus 18. Okay, let me justify why I've chosen those points. This is where it starts. Okay, we need some position where it starts. This is where we're asked to draw the motion diagram up to that point. And these are the points where it changes direction. Okay, we're not really interested in any other points, just where it changes direction. So here's what a motion diagram is, right? It's a horizontal axis. I'm going to say that's where we start, that's the point of origin. It moves, the furthest it goes to the right is 7 meters. The furthest it goes to the left is minus 25 meters. And then there's this minus 18 meters in here. I'm not drawing it perfectly to scale, but that's okay. And so what's going on with this object, right? Let's sketch it and show you. Here is where it starts. And it starts here when time is 0. Okay? And initially it's moving to the right. Okay, initially it's moving to the right, and after 1 second, when time is 1, its position is 7 meters. All right, so we're just plotting that point there to show you it's traveled along there. And we can see it has positive velocity, that means it's moving to the right. Okay, but here it changes direction and it starts going to the left, right? And so it goes all the way to the left until we get to this point when time is 5. Okay, we have positive velocity, we're moving to the right until time is 1. Then we have negative velocity between time is 1 and time is 5, we're moving to the left. All right, and then it changes direction there again, and it starts moving back to the right until time is 6, where it stops there. Okay, that's where we're asked to stop the diagram. We could demonstrate that it's just going to keep going that way forever because there's no more routes. Okay, that it has positive velocity after that point. Okay, so that's the motion diagram. Now, its displacement after 6 seconds we saw was 18 meters. So after 6 seconds, it's now 18 meters to the left of where it started. Okay? But the question is, how far has it traveled in total? What's its total distance? So what we can see is from here to here, it's traveled 7 meters. Okay, that's a distance of 7 meters. How about from here to here? All right, it's traveled 7 meters back. I mean, they're the same. All right, and then from this point to here, that's 25 meters. All right, from 0 to minus 25, that has a distance of 25. So how far has it traveled so far? Well, it went 7 that way, and then 7 back that way. So 7 plus this 25. And then it's gone from 25 to minus 18. That's another 7 in there. So we've got 7 plus 7 plus 25 plus 7. So what's that? 14, 21, 46. So to answer total distance, okay, so the motion diagram helps us to figure out how much it's moved to the right, how much it's moved to the left, so we can determine the total distance that it's travelled. So let's do a really quick recap here of the skills that we went through. Firstly, we used calculus to differentiate, find the velocity function and acceleration function, and draw their sign diagrams. You can use your calculator to support you there. Then we said, when does it change direction? Well, an object changes direction when the velocity sign diagram changes direction. Okay, so that's where we got time is 1 and time is 5, and we found the respective displacement straight off the calculator. Okay, we're doing a y calc when the x value is 1, y calc when the x value is 5 gives us the position. Speed increasing when these have the same sign, velocity increasing when acceleration is positive, and then the last one was to draw the motion diagram. We chose these points, where it starts and where it finishes, and then where it changes direction. You need those points on a motion diagram. And what is it? It's just an axis. We've got the point of origin, moving to the right, moving to the left, and then putting in its distances to calculate how far it's travelled in total. Really good. So 15E.2 today. Let's just work through that one. We've got 2 exercises to go. So yeah, you guys get stuck in, and I might write up what our plan is for the next 3 weeks leading up to the exam.